What if I told you that this ordinary-looking rock could power an entire city? Deep beneath our feet lies uranium, the backbone of nuclear energy. Today we're going to go on an incredible journey from mine to reactor, discovering how raw rock becomes the fuel that lights up millions of homes. This is the story of uranium, and it's more fascinating than you might think. Let's start with the basics. All right, what exactly is uranium? Picture the periodic table's heavyweight champion. It's element number 92. It's naturally radioactive, and it packs more energy punch than any other element. To put this power into perspective, here's something mind-blowing. This tiny uranium pellet contains the same energy as 3 tons of coal. That's why nuclear power plants can generate massive amounts of electricity without producing greenhouse gases. But here's the catch. Uranium comes in different flavors called isotopes. U-235 is our star player for nuclear power, while U-238 is more like its laid-back cousin. The trick is getting more of that powerful U-235. Of course, working with such a powerful element requires incredible safety measures. To handle this radioactive material safely, workers use sophisticated detection equipment. Handheld radiation detectors, about the size of a TV remote, constantly monitor radiation levels. Fixed radiation portals, standing 8 feet tall, scan every vehicle and container entering or leaving the facility. These detectors are so sensitive that they can pick up radiation from a single uranium particle the size of a grain of salt. Now that we understand what uranium is, let's explore how we find it. The process requires specialized equipment before we even start digging. Modern gamma-ray spectrometers, devices about the size of a briefcase, can detect radiation signatures up to 50 feet underground. These highly sensitive instruments must be calibrated daily for accuracy. Once uranium is located, there are 3 main ways to extract it. Let's start with open-pit mining, where the workhorses are massive wheel loaders. These giants stand 22 feet tall, about as high as a 2-story house. Their buckets can scoop up 36 cubic yards of material in one single bite. That's enough to fill a standard bedroom. But before these massive machines can start working, we need to break up the rock. That's where powerful drill rigs come in, boring holes 12 inches wide and up to 54 feet deep. These holes are filled with explosives to break up the rock. Due to the extreme hardness of uranium-bearing rock, the drill bits, tipped with ultra-hard tungsten carbide, must be replaced every 48 hours. When the uranium lies deeper underground, we have to use a different approach. This is where specialized boring machines called roadheaders come into play. These 100-ton monsters use rotating drums studded with tungsten carbide picks to carve through solid rock. Each machine can cut a tunnel 21 feet wide and 16 feet high in a single pass. Safety is paramount in these underground operations. Massive ventilation fans, some measuring 8 feet in diameter, push fresh air through the tunnels at a rate of 240,000 cubic feet per minute. These industrial-grade fans are powered by 500 horsepower electric motors and run 24/7 to keep miners safe from radioactive radon gases. The third and most innovative mining method is called in situ leaching. Instead of digging up the earth, this technique uses a network of injection and recovery wells. The injection wells, typically 6 inches in diameter and lined with corrosion-resistant PVC pipe, can reach depths of 1,000 feet. High-pressure pumps force the leaching solution into the ground at rates of up to 3,000 gallons per minute. At the surface, industrial reverse osmosis units larger than shipping containers filter the uranium-rich solution. These units are special membranes that can withstand the highly acidic environment while removing 99.9% of impurities. Now you might be wondering, where in the world is all of this uranium coming from? Well, let's take a look at the global powerhouses of uranium production. Kazakhstan leads the pack, producing about 40% of the world's uranium. Its largest mining facility uses over 400 injection and recovery wells spread across 35 square miles. Kazakhstan is a pioneer in situ leaching and a trendsetter in environmentally conscious mining. Now, not far behind is Canada, with some of the highest grade uranium ore in the world. Their advanced mines use specialized jet boring systems, essentially giant water cannons that blast ore with water pressurized to 2,500 pounds per square inch. When we say high grade, we mean their uranium is exceptionally pure, like finding a gold nugget instead of just gold dust. Rounding out our top 3 is Australia. With its massive deposits and state-of-the-art mining operations, their largest mine operates the most extensive underground ore handling system in the world, with crushers and conveyors that can move 60,000 tons of material per day. Now comes the most fascinating part of our journey: transforming raw ore into nuclear fuel. This is where engineering meets chemistry in an impressive display of industrial precision. The transformation begins with primary jaw crushers, massive machines with steel plates that can exert up to 350 tons of pressure. These crushers, weighing as much as 400 tons, break uranium ore from boulder-sized to 6-inch chunks. From there, cone crushers take over. These machines are basically giant steel funnels with a rotating inner cone. The gap between the outer shell and inner core can be adjusted down to millimeters for precise sizing. They spin at 700 RPM and are powered by 1,000 horsepower motors. The final stage of size reduction happens in rotating rod mills, measuring 12 feet in diameter and 20 feet long. Each mill contains 100 tons of hardened steel rods that tumble like a washing machine. The rods, ranging from 1.5 to 4 inches in diameter, grind the ore into powder finer than beach sand. With our ore now reduced to a fine powder, the chemical processing can begin. The powder enters massive leaching tanks, each holding up to 50,000 gallons. These tanks are lined with rubber and high-grade stainless steel to withstand the corrosive mixture of sulfuric acid and hydrogen peroxide. To keep this mixture properly agitated, computer-controlled agitators with 20-foot titanium blades keep everything moving precisely at 120 RPM. Steam jackets heat the tanks to 50 degrees Celsius or 122 degrees Fahrenheit, while sensitive pH sensors continuously monitor the acid levels. Third, purification. Next up comes the purification stage, where the uranium-rich solution moves through a series of mixer-settler tanks. These 1,000-gallon vessels use special organic solvents that bind only to uranium molecules. High-speed impellers spinning at 1,200 RPM create perfect mixing conditions. The solution then travels through pulsated extraction columns, standing 30 feet tall, which use compressed air to push it through perforated plates. Each column processes up to 500 gallons per minute, separating uranium from other metals with 99.95% efficiency. Now we're ready to create what's known as yellow cake. Ammonia injection causes uranium to precipitate in 5,000-gallon crystallization tanks. The resulting yellow cake slurry passes through centrifuges spinning at 2,400 RPM to remove excess water. To prepare the yellow cake for the next stage, multiple hearth furnaces, standing 3 stories tall, dry it at 800 degrees Celsius or 1,472 degrees Fahrenheit. These furnaces have computer-controlled arms that slowly move the material through 6 different temperature zones. We've now reached the crucial enrichment phase. This process uses thousands of gas centrifuges arranged in cascades. Each centrifuge stands 40 feet tall but only 8 inches in diameter. Their rotators spin at 100,000 RPM. It's so fast that the outer edges move at nearly the speed of sound. The final step transforms this enriched material into usable fuel. Hydraulic presses exerting 30 tons of force compress it into pellets. These pellets are then sintered in furnaces at 1,750 degrees Celsius or 3,182 degrees Fahrenheit for 24 hours, creating a ceramic material harder than steel. Throughout the entire process, safety remains the top priority. Workers wear 3 different types of radiation monitors, including a personal dosimeter badge, an electronic dosimeter that provides real-time readings, and a special breathing zone monitor that checks for airborne particles. From deep underground to reactor-ready fuel, uranium's journey showcases human innovation at its finest. Each step combines precise engineering with rigorous safety measures to create one of the most powerful energy sources. And if you found this journey fascinating, well, don't forget to hit that like button and subscribe. Tell us in the comments which piece of equipment you're surprised by the most. Hit that notification bell and catch our next fascinatingly entertaining video. Thanks for watching.